Telegraphy, which involves part of the presentation,
Oh,
is,
well,
the
okay,
sending,
we'll cover it.
is the sending of messages by wire and later by radio by using a representational code where the code represents individual letters. You spell out your messages as letters. And we'll get into some more detail as we go along. The instruments, the common ones are the key, the register, the relay, and the sounder. And these are in the order that they came into service in telegraphy. That may surprise some people. First thing we're going to do is go over a little bit of basic physics. This is a drawing of the electromagnet used in telegraph equipment. You get the current flowing through this, and the current varies between 1/4 of an amp and 60 hundredths of an amp, anywhere in that range depending on the instrument. And the magnet will draw the iron bar shown, yes, good, it shows in there, shown here on top of the element that's going to draw. The iron bar is attracted to the electromagnet, and that's what does our work for us. And another little wrinkle I'm going to point out while we're on this slide is one of the sounders you're going to see pictures of in the course of this is both a 400 and a 100 ohm sounder. Now, if you wrap your head around that and apply a little Ohm's law, you know it's 400 when the coils are in series and drops to 100 when we wire them in parallel. The only thing we have to be careful of when we rewire them in parallel is that we don't wire them so they cancel each other, because then it doesn't work at all. Okay, but that's the only caveat there. So if you need to, and many, for instance, railroad shops did this a lot, they could take one sounder and convert it to roughly 1/4 of its previous value by wiring the coils in parallel, and that's the only change they had to make. So it's just, you know, a good thing to know about them. All of the current, at least initially for these early telegraph systems, were provided by this bad boy right here. It's called a gravity battery. You fill a jar, it's about 6 inches across and about 8 inches high, half full of water, and then you dump in a considerable quantity of what was called blue vitriol. And that's a chemical that breaks down into both a sulfate and a positive side, and by gravity alone they separate in the jar, and that's why the jar was called a gravity battery. So they formed 2 layers of fluid in the jar. The battery was commonly called, by the people who had to work with and on them, a crow's foot battery. This electrode right here looked to them enough like a crow's foot that it got that name and it stuck. This star-shaped gimmick down here is a copper plate electrode, and the wire that you see here has to be insulated because it passes through the opposing solution, and it would internally short the battery if it weren't well insulated. So each of these batteries produces almost exactly a volt. Now, it depends on the strength of the solution at the exact moment when you're going to check it and all that. But so each volt you need is another one of these batteries. Picture in the early days of telegraphy being the poor sod who had to maintain 100 or more of these puppies in a row and keep them working all the time in order for your telegraph office to function. They stank. They gave off some rather noxious gases that could be somewhat corrosive and also probably weren't very good to breathe. So a lot of young men probably had their lives shortened by taking jobs with these things. But it was the first battery generally used for telegraphy. Now, the Davidson battery and others quickly became in use, and a lot of that happened because of the Civil War, because one thing a gravity battery won't tolerate is riding around in a signal corps wagon. As the fluid sloshes and mixes, the battery became useless. So you couldn't use these in motion. So other batteries were quickly developed as an answer to those sorts of needs. Samuel Morse actually developed, invented, you'll get some arguments on this, but everything I've seen says it's true. He invented the electromagnetic telegraph. The printing telegraph, the first one. The only competitor to that claim is a needle telegraph that used a needle much like you have in any directional meter movement today, that went to the right or left on a board that was in some use in Europe. But it was quickly passed by when this was developed. Even the Europeans quickly developed the electromagnetic mechanical telegraph. It's worth knowing that Morse's patent was on an electric printing telegraph. And that becomes important for a couple of reasons. Now Morse, when he went to develop the code that was going to be used in this, he assigned a number to every word in common usage in the English language. The resulting document had about the bulk of a modern printed telephone directory for a pretty large metropolitan area, okay? It just was unbelievably cumbersome, and to develop any speed with that is going to take a miracle. Well, Alfred Vail, who was Morse's engineering assistant and actually built and devised all these devices that Morse came up with for him, took one look at that and his engineering heart said, no way. And Alfred came up with a simple alphabetic substitution code that became the Morse Printing Telegraph Company code, hence Morse Code. I try and remember to always call it the Vail Code. Morse had nothing to do with it. Alfred Vail devised it. It was his sole work product, but since he worked for the Morse Printing Telegraph Company, like anybody else who did work for hire, the patent went to the company, not to the individual. So that's how that worked. And that's how they had to do it in order to protect themselves from the other people who very much wanted into this brand new and very lucrative business. I want you to imagine, if you can for a second, the fastest way you had for doing a transaction at a distance was the U.S. mails. Now, to the West Coast, that was a week from this part of the country. A full week, even after the Intercontinental Railroad. Back when telegraphy was first developed, that was a little bit ahead of that. It was much longer. Things went by ship and stagecoach and things like that. So it could take weeks just to get an agreement on how you were going to do something. And then you had to execute it, and notaries and other such people were very important because they would attest for you that the guy who signed this document really was the guy you thought you're dealing with, and so forth. That's where that whole system that we now look at as archaic, but elements of it survive, arose from doing business by distance through the mail. Imagine what a tremendous and transformative thing it was for the owner of a company that needs paper made to be able to contact from here, from the Washington, D.C. area, a mill out in Wisconsin, and have the blasted paper that he specified on a rail car heading his way in less than a week. I mean, it changed the whole mercantile and financial ballgame for the whole country. It's one of the major things that allowed us to develop ahead of a lot of other places. Now, it's important to know, though, that the Morse Code, or rather the Vail Code, was developed by Vail running out and buying all the newspapers that were available in his area on that day, and then painstakingly counting every letter in those newspapers. How many times does an E occur? How many times does a U occur? And so forth. And after he had made his count, he assigned the simplest characters to the most commonly used letters and saved the more complex characters for the least used letters. That is why during World War I, when American telegraphers went over to Europe, the European telegraphers were blown out of the water by how much faster they were, because first of all, they weren't dealing with several languages, which European telegraphy had to deal with, and their coding was simpler. They had not tried for so many punctuation marks. They didn't have the burdens the Continental Code had. And the Continental Code is what later became the International Radio Telegraph Code. So the one we've all learned, we call it Morse. It isn't. It isn't Vail, it isn't Morse. It's International Radio Telegraph Code. An important distinction. How many of you were here when Mona Singleton did the presentation on the women telegraphers of World War II? Remember that? Great presentation, and a couple of veterans were able to attend. And one of them sat down for us, and Bill Fate, at her request, she said, "Who's your hot lick?" And I fingered Bill right away. And Bill sat down and rapped off some telegraphy. Not only did she print it in real time as fast as Bill could send it to her, but she tapped it out in Vail, North American Landline Telegraph Code, with her other hand almost in real time. Because as a coast operator, she had to correspond with ships and then send their message on shore. On shore, it had to go by Vail Code, American Landline Telegraph Code. On the ships, it went by Continental, which had become the International Radio Telegraph Code. I asked the lady before she left, I said, "How on earth did you learn to do that?" And she says, "Well, when you have a merchant captain begging you to get him Army Air Corps cover so that the Nazi submarine will have to dive and he can outrun it and not get down to Davy Jones with his entire crew, that's an incentive." And I just couldn't believe what high pressure must have been on those coast operators to get that message, because in the 40s, telephone was not yet reliable long distance at all. Telephone connections would often be unreadable. You know, it'd be like the worst kind of half-baked tuning on an SSB signal. You know, Donald Duck may be in there someplace, but not intelligence. So that's the kind of challenges those women who were coastal telegraphers during World War II overcame. And it was tremendous. I ought to rope Mona into coming back and doing that one again. It was a great, great show. Okay, so we leave Vail, and it's worth remembering Vail because he built all the stuff Morse came up with. He and Morse would sit down and, well, I've got an idea for a device that does this, and Vail was the one that actually had to produce it. So he actually built these devices after Morse had one of his brainstorms. This is the Morse alphabet as printed by the Vanel Company, a major manufacturer of telegraph instruments. And you'll notice it's got the numbers 1 to 0 and a limited set of punctuation, but it's certainly not an exhaustive set of punctuation even for English. And there was going to be no lowercase because Vail thought that was a waste of time. And it continued that way right through, well, Badeau didn't have lowercase, or did it? No. So it wasn't until EBCDIC and ASCII and later codes that they had the ability to do lowercase in long-distance communications. Even Badeau, which was a 5-element teletypewriter code, did not do lowercase. So this is a Vail correspondent, Vail's first design for a telegraph key. Now, there are a few things that many of us are used to seeing that are absent here, and I'm sure you'll notice what, but this was the first key that allowed Vail or anybody else to rapidly open and close the circuit so that code could be sent by turning the current on and off. All the early keys that went into large-scale production were called legged keys. They had bolts that held them to the desk, and those bolts were also the wire binding post for the wiring. The wiring was done under the table. Well, that's not surprising, since on some circuits the voltage go up to 400 volts DC. And yes, it was ground because it was using ground return, so at 400 volts DC relative to the earth, even though it was only 60 milliamps, you didn't want to get across that. It was a very unpleasant experience. So this is called a Camelback Key, which identifies it as one of the earlier keys. I do not know why they started out this way. Never learned the reason these were so popular, but eventually, because of the greater difficulty in machining and producing these, they went by the wayside. But all of the early keys were Camelback. They have a hump in the left. Now this is one of the earlier registers. Notice this hole right here in its base. Can everybody see that? What that's for is the weight and the cord that supports the weight that kept the register running. The register was a clockwork mechanism that did only one thing. It moved a paper tape at an even rate once it started rolling. That was its job. What put intelligent information on that paper tape was a metal stylus that was moved in the same way all other telegraph apparatus was moved, by the magnetic flux of the telegraph electromagnet. Initially, it was just an impression, a score it made into the paper tape. And paper tapes were repeatedly used because, you know, they were trying to be economical about it. But that's where we get the terms dot and dash. Telegraphy was originally done as a printed code. It was received visually. The terms dot and dash were not a later degradation of teaching technique or any of the things you'll hear, even from some very good instructors. It was how we started out with telegraphy. It was a printing telegraph system. But just by this picture, even though you can't see it in great detail, you can see that that's a complicated little monster. They didn't turn out to be the greatest thing on God's green earth for receiving. And they were a little bit greedy in terms of how much current they wanted to operate. So Morse came up with this kind of thing. This is a much later design, but representative. It's a relay. Just like most of the relays we use for all sorts of things, you know, like changing antennas. Many of us use line relays to change antennas out at a tower, stuff like that. And the relay's job was the contact here and the one that you can't see because of the spring post hiding it. Those were attached to the coils of the relay. And the contacts that were on the armature, which is, you can see the very tip of the armature here, were what did the work for you. So here's your armature, all right? And notice that it's upright and balanced when it's real. This diagram shows a much larger range of play than would normally be used so that you can clearly see things in it. But really, the amount of travel in a relay was kept very short so that it could operate quickly. And here's something I want to point out that nobody misses. Notice this. It's an ivory tip. That was the first material that was readily affixed to the end of a screw that would insulate well at telegraph voltages. That screw had to be insulated from the armature, or the armature wouldn't do its job. But this screw over here was conductive. Now originally that was done with two separate posts, one of which was attached firmly to the conductive base and one of which was isolated from it with natural rubber or compressed paper or a bunch of other remedies. So one post would be the terminal post and the other post would be the common post, and the two terminals would be wired the same way. This is a later design, but you can see at least that the armature is much smaller and lighter than the moving parts of, say, a register, and even smaller and lighter than the next step in the game. But here's something worth noticing. Now this is a local circuit. Here's the sounder that the telegrapher is going to listen to, and here's the battery. And this diagram is inaccurate in that it shows two cells. Local batteries in individual stations were one cell. They were exactly like the battery I showed you in the previous slide. And that practice continued right up and through the 1930s. Because when you had a shack beside a railroad that was a signal station, or a tower beside a railroad, there wasn't necessarily any electrical service available to that location. And it was not in the railroad's interest to build power generation there. But if all you have to power is a 4-ohm sounder, divide, you know, your amp by 4, and you've got the quarter of an amp it takes to run the sounder. It runs on 250 milliamps, a local sounder at 4 ohms. So it continued in service right through the 1930s, and then little converters that you can now find here and there in free markets came into use, and a lot of electrical service was necessities of the war effort. A lot of places received electricity that hadn't had it up till then because of the need for it during the war in World War II.
Tom, question about the battery.
Yeah.
So those are not rechargeable batteries, right? As long as you kept putting the right chemicals in it, they constantly kept charging.
They are primary batteries. And the definition of a primary battery is one that gives its all to the task. Once it has done its work within the limits of the chemical that you provided into it, it's gone, it's done. You recycle it. Now, the nice thing about the gravity battery, the reason it continued to service so long, it was so easy to service since the two fluids divided themselves by their specific gravity. When you'd run down, you'd add a little more water and a lot more of the vitriol, and bingo, you'd have a full battery, and after about a day, the gravity separation of the two fluids would occur between the blue vitriol and the water that was, in the area where the zinc is, and the battery again be producing a volt. Now the battery wasn't real generous with the voltage it produced, but it was wonderfully generous with the current. It produced plenty for the job, and that's one of the reasons it worked well for so long. But initially, they were the only batteries you had. You need one battery for each volt you needed for anything. And that's why the local sounders are only 4 ohms, so they could run on only 1 volt at a quarter amp. Now, back to this local circuit. The dotted line represents a circuit that only exists in the station. And the solid lines represent the wiring of the actual telegraph line and the way it was managed. Now, I'll go over a few more details of how it was managed, but it's important to know that these 2 contacts on the relays were dry. Now, there are relays that I won't go over in detail tonight that were deliberately made by the addition of either a sound box or a drum to be louder so that they could do both jobs. And in some uses, that relay would be a relay and key on board, and it'd be a station. You wouldn't have a local battery. A great example of that would be a caboose set or a wrecking set. A caboose set was carried because that particular train's consist had to go through an interlocking, and it was often rigid policy that they had to tie into an existing telegraph drop before the interlocking, and again confirm their permission to use it with both operators on either side of the interlocking to lower the risk of a collision between trains. This was a tremendous boon to railroading, as some of you who are enthusiasts know, because it allowed the management and movement of trains to get a heck of a lot more efficient. So any given set of tracks could move a lot more freight. When any train ran behind time on the timetable system, where they couldn't communicate between stations effectively, the whole timetable got messed up, and it was very hard to bring it back into line. So the whole railroad on that line could get very bungled up before they could get to a position where they could, and they had procedures for that. Everybody holds in place until our errant train arrives at a place we can get them off the track. And that crew, under the dictatorship management of the day, would stay with that train until everything was straightened out, because it was their fault. So the local battery was one of the single cells I told you about before. And the relay, mainline relays, and almost all of them were mainline, drew only 60 milliamps of current. So the line only had to carry 60 milliamps at a voltage big enough to overcome, large enough, high enough, to overcome the resistance of the wire and all the relay coils in series on the line. Each station on the line was a set of relay coils. The keys were so frequently and often used that they had zero resistance because they were always polished by the motion of use. You didn't have to worry about that. And the relay contacts were in the same shape. They burnished themselves by bouncing back and forth in use. So they were very conductive. But the coils, on the other hand, were a fixed resistance that had to be overcome. We'll go over this a little bit in a few minutes. Now the sounder, it wasn't long before the telegraphers. Initially with registers, there was a telegrapher to read that darn tape, and there was a copyist or clerk that would take down the messenger as the telegrapher read it. No matter how fast that tape was going by, it turned out to be too difficult to do 2 visual tasks at the same time. One to read and one to write down. So 2 people did the job to make maximum use of the line. The labor costs were appreciable. The telegraphers found themselves anticipating the next letter, but because of patent issues, the operating company strongly discouraged them from doing that. Their patents were on a printing telegraph system. If they started copying by ear, there was a danger that it would breach the patent. Now, that was eventually overcome, and I don't know the details of how they overcame it, but I suspect it was Morse's development of the relay and this local circuit that I showed you before, and his patent on that saved his butt, because it then didn't matter what the line relay was controlling. He still had a patent on the local circuit that precluded its use by others. So this was devised, and here's a diagram of them, as a much cheaper way of receiving, because a single operator, the telegrapher themselves, could write down the message as it came in. And the other thing about it is that mechanically it's a very simple arrangement. It has there's one moving part in this whole thing, and that's this thing right here, and that's called the hammer bar. Because all it does is hammer all day. And this stand on which it hammers is called the anvil, because it resembled a common fixture of everyday life during that period, the work of a blacksmith. Every town had one. They had to. Things had come to a stop without. Here's your return spring. Whenever the electromagnetic flux is absent, it throws the hammer up, making one kind of click. And when the electromagnetic flux returns, that pulls this iron bar, which you can see in the plan view here, down toward the magnets, and it falls to the limit set by the travel adjustment screw that you see the top of right there, and maybe you see the bottom of right here if your eyesight's real good. So it was much simpler than the register. Registers consumed paper, lubricant, maintenance, and they were expensive to acquire in the first place. So it's a natural development that as soon as telegraphers realized they could copy by ear, the register for general use was doomed. They had to think of a way to get around it because it was just so much more efficient to receive by ear. But many of you will have seen, at least in the movies once in your life, a telegram where strips of paper are glued to the form that the telegram is received on. And that came out of teletypewriter use, where the strip came out of the teletypewriter, was cut into strips and glued, so that you got the telegram exactly the way the office received it. That practice goes way back to the registers, which continued in use for one purpose: financial transactions, especially high-order transactions. The telegrapher would write the letters under the paper tape so that the image as actually received was sent to the financial institution. This allowed the financial institution to trust it, just like they trust the man or woman who'd sent it, because they had the original copied tape glued to the form above the telegrapher's work. So that was the origin of the practice of taping the message. This device is a resonator. Much like the sound box on a guitar, it vibrates in time with the hammer bar, and because of the way the opening's pointed, reflects the sound in its direction. Much like our beam antennas, it's not actually amplifying the signal, but it's concentrating it so much in a single direction that it makes it stronger effectively. Instead of having it go 180 degrees round or own, it's going to go in general in about 45 degrees where the resonator's pointing. But as you'll see in a minute, that wasn't the do-all and end-all. This is a Prince Edward tobacco can, and that's because the telegraphers, especially as they aged, had trouble hearing their sounders, so they'd stick a tobacco can in between the anvil bar and the end of the resonator or the back of the resonator with the top open, and it proved an even more effective amplifier for the sound. And why that became important was, oh, by the way, in normal use, in most railroad stations and so forth, sounders would be, resonators rather, a sounder in a resonator would be positioned on top of a candlestick stand. And when the station agent needed the thing, he'd just pull it to it. It was on a flexible cord anyway. Okay? And slightly later than the period I'm talking about, that could be plugged into any one of several lines. Most railway stations had at least three. They had a Western Union line, or whoever the operating company were. There were several for a while. They had a railroad line, and then they had a dispatcher's line, a railroad business line, and then a line for the dispatcher to manage movements. So there'd be three mainline sounders, and he'd plug the sounder in when he heard his station called, or she, many telegraphers were women, especially after the Civil War, when there was a shortage of telegraphers in the cities with the war going on, and the military telegraph service of the Union offering wages that very few young men could resist. They abandoned their post with Western Union and American Telegraph and the Postal Telegraph Company to go to work for the military telegraph service. They were not soldiers, but they were paid very well. And as such, it made them vulnerable to certain excesses of the other side when they were captured. But after a while, word was delivered to the Confederacy that the Union was prepared to treat their telegraphers the same way if they started being as brutal to telegraphers as they had been initially. They were going to make telegraphers a separate class in the military order of things, not protected by the rules of war if the South didn't knock it off. And that's the same way they resolved several other disputes. The next thing that came into use to make receiving easier is called a swing arm resonator. That three-part arm, built by a company that still exists, OSI White Company of Massachusetts. They build some really nice lamps and both retro and modern light fixtures, and fixtures that go in machines to provide lighting to machine work and all sorts of things like that. So they still exist. They even provided me with a part for a swing arm, which took the owner had to order the part made by the shop from a diagram they still had. Didn't even gouge me for it. I was amazed. But that thing could extend from its base a little more than 2 feet. Why would they need to do that? Well, this is why. This gives you an idea of the age range of telegraphers, because this young fella here, if he's more than 16 years of age, it would be a tremendous surprise to me. And they're all so close to each other, each working busy circuits, because an office with this many telegraphers had a lot of busy circuits. And they had to differentiate their circuit's noise from every other circuit. So this allowed them to move the resonator right up next to their head conveniently, and yet if it were in the way at any time, they could push it back clean out of the way conveniently and do their adjustments, repairs. In the latter days of telegraphy, all copying was done with a mill, which is nothing but a mechanical typewriter that has no lowercase. There was no reason to put the lowercase mechanism in a mill, so Royal, that made the first ones, didn't. They gave the Western Union Company a better price because they were mechanically less complicated. And that partially made up for the discount Western Union demanded on orders of hundreds of typewriters. As you can see how close these individuals have to be to their sounders to make out their signal in a crowded office. Now the closed circuit telegraph line, the North American style of line, is represented by this line diagram. There is an error in it that I'll point out right away. These are circuit closers, this part of the diagram right here. And if more than one of them were open at any given time, nobody could talk to nobody. You just couldn't. Current wouldn't flow in the line. The normal condition of the circuit closer on a North American telegraph line is closed unless the circuit is engaged, and then the telegrapher that needs to send opens his closer, sends an attention signal, sends the station signal of the station that's supposed to receive the message, and recloses his closer or her closer so that the other telegrapher can answer and confirm that they're ready to receive. Just leaving his own closer open would cripple the line. In Europe, they did something different that I'm not going to go into. It was a later development. It had its strengths, but it also had some drawbacks, as you'll see when we go over troubleshooting. Stations served by either one line or several were all sort of laid out in the same general way. And that is, it was a single wire supported by insulators. And this is a picture to just give you some idea of how many different companies were making insulators and offering them for sale. The problem was the vast majority of the insulators were either glass or glazed ceramic. And boy, did those country little kids love those. Every hand or sling-thrown missile in the world the very satisfying shattering noise and shower of shards when you hit the target was too much for kids to resist. The railroads answered with what for the time was the phenomenal offer of a $10 reward for information leading to the arrest and conviction of those breaking insulators. It was a problem that was never actually solved in American telegraphy because of the parsimonious attitude of the operating company towards cost. It was penny wise and pound foolish. The white flint insulator was developed by a man named Elliott. It's got feldspar, flint, and something else in it. I forget the details. But it's damn near unbreakable. He demonstrated it by firing pistol balls at it. And it would not give in. The pistol ball would flatten against the insulator. So this was a very effective, now admittedly they weren't modern steel bullets, they were lead balls, but still, this was a very convincing demonstration of how durable they were. And they also had a great design in that there were several skirts under the edge so that moisture could not form a continuous surface under the bottom edge to lead to leakage of current out of the line.
What were they made out of, Tom?
They were made out of flint and I forget the other two ingredients. One of them I thought was feldspar, but I'm not sure. My notes are refusing to show up on my machine right now, so I can't confirm that. But I can answer it afterwards by getting out of the slide presentation for you, because I've got it on my notes. Those didn't see universal service. Sorry about that. All right. At each station, this gimmick, which is about 8 inches long, is called a break iron. And it was a way to mount two insulators very close together on a single cross tree or on a single bracket. A bracket was a piece of wood that got nailed into the side of a single line pole. Rather than put a cross tree up there if you only got one line. You nailed a piece of wood to the side that had the threads on it to receive the insulator and kept it simple. But wherever you had a station, you had to have a brake iron because there was air between this, and the drop wires ended up at a wall bracket on the station wall, always two of them, but this was the nicest picture of them I could find. And then from there, they went into a porcelain or hardened rubber tube to go through the wall into the office, okay? At that point, they'd end up on one of the very many gimmicks, this is one representation of lightning arresters. Most of the early designs were brass plates or copper plates like this, brass preferred because it tarnishes less readily. And just like I burnish our ground stakes when we put them in at field day because copper oxide doesn't conduct anywhere near as well as copper does, it was important to keep these plates clean so that they conduct readily. Notice the sawtooth design in the edge of the plates. That was to provide a maximum length of surfaces adjacent to your ground plate that could discharge current. And the pointedness of the sawtooth design would cause the current to build up and break over readily and establish the arc needed for flow at that point. These three terminals down here are your east line, your west line, and your grounding electrode conductor that goes to the station grounding electrode. These two terminals are the inside loop of the station. Now this arrestor is undoubtedly in the condition it was in when it was removed from a station long denuded of telegraph equipment because the shorting pin here is in the position that connects the two lines to each other. And that's done when a station no longer has a telegraph operator, and of course later when it no longer had telegraph equipment, because the lines were being used by teleprinters. It was no longer necessary to have operators at all these little stations. You could connect either line to ground, you could connect the two lines to each other, and connecting them to ground was part of troubleshooting and testing. That'll come up in a minute. The later designs, these button plates could be screwed in and out by hand to adjust the gap between the grounding electrode and the plate. And that became important as weather would change, dampness, things like that. You could fault out the line if they were too tight in damp weather. And you need to open them enough so that the line would stop faulting out. But you needed to remember to readjust them as the weather dried out because you didn't want any more gap than absolutely necessary. They weren't the greatest protection in the world, but they were all they had. Later developments. Now, some of you in this room, whether you'll admit it or not, are old enough to recognize this. This came down in use out of telegraphy and was used in some of our older homes for telephones right up through the 60s. There are two fuses in the line. In telephone practice, the line was at the end of the fuses. In telegraph practice, the line was across the arrestor and the inside loop was at the end of the fuses. Because if you broke that line with a fuse, you took the whole line out of service in telegraphy. In telephone practice, you only take a single customer out of service. So that's why you could have the fuses in the main line in telephone, but not in telegraphy. It was not tolerable, so they were used the other way around in telegraphy. And the fuse was when things got rocking and that line lit up like nobody's business. It at least was less likely to set fire to the place. There's a rather famous event that's still studied today called the Carrington incident. It was believed to be, I don't know if they've ever confirmed this, a solar storm. And the only electric things in broad use when it hit were the telegraph lines. And those hundreds and hundreds of miles of telegraph lines served as antennas for it. Western Union records that have been preserved show that they lost over 100 offices to fire, and the damages across the entire company were phenomenal because all that wire gathered all that energy. So it's sort of like a preview of an electromagnetic pulse from an airburst nuclear bomb. Now that we've got 1 billion times more wire up in the air than we had back in the 1840s. Now this is a later version still of an arrestor. I actually own one of these. And this is the electrode plate. The electrode is this terminal. The grounding electrode conductor would be attached to this terminal right here. And this plate is a little thinner than it would need to be to actually contact the two line straps. Each of these buttons, or circular plates, is for these wire binding posts, and those were for the inside loop of the office. The inside loop would be terminated on them. And whether or not that insulated loop would be connected or not would depend on the placement of the brass pegs. You can see one of them's in place, but this one would need to be in place here to connect the inside loop to the line on both legs, okay? So it made it very useful as both a lightning arrestor, and now you also had a switchboard effect. There were more complicated versions of this built to serve several different lines. As I said, railroad stations often had 3 lines later on, just for the sake of the railroad, let alone anything else. So there'd be boards made up with 3 sets of straps, and 3 sets of buttons, terminals, and all of that, in order to manage that. But the beauty of the system was that once it's built, you can connect any inside loop to any telegraph line just by changing the arrangement of the pegs. Sorry, back one. Now, line layout. All we're showing here is the circuit closers, the key, and the coils of the relay. Unless you were right on top of the relay or it was a box or snare drum relay that I referred to earlier, you were going to have a heck of a time copying off of this. The terminals of the relay, the dry terminals, would control the actual sounder you'd copy from. And that nice hard click produced by that 1/4 amp flowing in the sounder was what was convenient to copy. And as you got older, there was the Prince Albert tobacco can, and you convinced the railroad to send you out a swing arm sounder so you can put it right by your ear. But notice, and once again, same problem, only one of these circuit closers can be open at any given time, and that key controls the circuit. Open to when the line's crippled. Now when you have line trouble, well, the most disastrous line trouble was a break between 2 stations. Okay, because there was your station agents, your telegraphers couldn't do anything about it. The line crew would have to go find it. But the beauty of the American system was what you see here. Each station on either side of the break could strap the broken side of the line out of the circuit and strap ground into the circuit and be able to speak to at least one terminus the same way they always did, by ground return. And by the fact that the terminus stations could hear from this station and this station, they could tell the wire boss where to send the repair crew. And by other paths through other towns, they could get messages to the repair crews. You're going to go out to Singleton Gap and look there, and then procedures I won't bore you to tears with that changed a lot over time were used to figure how far out it was likely to be. And then it was a matter of riding the line on horseback and finding the break and fixing it. That's the sketch. That's the early history of telegraphy, wireline, telegraph signals borne by wires in this country. But Bruce has brought in some equipment that I'd invite you all to go and see, because it's the real deal. Those are actual telegraph instruments. You'll recognize them from the slides. And can you get the...
You might be able to talk to Vic.
Great.
You were relying on earth ground to
Yes.
the circuit.
The return is always earth. And notice something
Is
else.
that a problem though, that some stations out in Arizona not getting good ground? I don't know.
You just kept going until you got one. Telegraphers got very inventive in their techniques. Laborers would sometimes have to dig a well. They'd get water and put the electrode in the damn well, so the station had not only its water well, but an immersed electrode to get effective communications. But keep in mind, the intermediate stations only needed that when something was wrong. Only the two terminus stations needed a good one all the time. And they weren't likely to be in the 7th hill above Sedona, New Mexico. They were likely to be down in some major city. But notice the batteries. Pretty quickly, the normal practice was to have a battery at each end of the line in the terminus stations. One down, one up. What do I mean by that? At one end, you ground the positive. At the other end, you ground the negative. And between the two batteries, they make enough voltage to overcome the circuit and coil resistances in the line. Why that's a good thing is when the line breaks, you still have a battery at each end and ground return to make a complete circuit. So what happens when the line breaks is every telegrapher had the duty to connect two sets of receiving instruments. A second relay, if he or she had one, or a line sounder, if that was the remedy, between each side of the line and earth. Then the terminus stations begin it themselves and call the next station, and when he gets the terminus station signal, he normalizes his line. If it holds to the next station when he normalizes it, if the sounder stays pulled in, the wire's good to the next station, they signal him, they call the next station after he normalizes. If they reach her, they call the next station until finally a station doesn't answer. Well, that last station that tried to normalize will go on that side back to ground, and those stations will be able to continue to communicate. And it happens on both sides of the line. Both terminus stations now know between which two stations this fault is, and they can communicate that to the wire. Thank you for your time. Hope you enjoyed it.
Dots and dashes?
Yeah, I'm cheating. I'm not using a key.
Notice the key is closed.
Well, it's not on the computer. But I know I'm going to close the circuit. I'm just using the computer now because my telegraphy skills in American voice are really bad.
And